Welcome to this scientific lecture on droplet lenses. Today we will explore the fascinating physics of how simple liquid drops can function as tunable optical systems. Let me start with a question. How can a droplet, something as simple as a water bead, act as a lens? The answer lies in the interplay of three fundamental physical phenomena: curvature, refractive index, and gravitational forces. First, let's understand why curvature matters. A spherical interface between two media with different refractive indices naturally acts as a lens. When light enters a curved droplet surface, it refracts according to Snell's law. The curvature causes parallel rays to converge, creating a focal point. Snell's law governs refraction. N1 sine theta 1 equals N2 sine theta 2, where N represents refractive index and theta represents angle of incidence. The focal length of a droplet lens depends directly on its radius of curvature. A smaller radius means stronger focusing power. For a spherical interface, the focal length f equals r divided by n minus 1, where r is radius and n is refractive index ratio. Now let's examine how refractive index determines optical performance. Different liquids provide different focusing capabilities. Common droplet lens materials include water with N equals 1.33, glycerol with N equals 1.47, and silicone oil with N equals 1.52. Higher refractive index provides stronger focusing. Here's an important question. If higher refractive index gives better focusing, why not always use materials with the highest possible N? The answer involves trade-offs. High refractive index liquids often have higher viscosity, making dynamic tuning slower. We must balance optical performance with mechanical response time. Surface tension is the critical force that maintains droplet shape. This molecular cohesion creates the spherical geometry essential for lens function. The Young-Laplace equation describes pressure difference across curved interfaces. Delta P equals gamma times the sum of 1 over R1 plus 1 over R2, where gamma is surface tension coefficient. Surface tension acts like an elastic membrane, pulling the liquid surface inward uniformly. This creates the natural spherical shape that minimizes surface energy. For droplets sitting on a surface, the contact angle between liquid and substrate becomes crucial. This angle determines the droplet's final curvature. Young's equation gives the contact angle. Cosine theta c equals gamma sg minus gamma sl, all divided by gamma lg, representing the balance of interfacial tensions. Gravity plays a competing role. While surface tension favors spherical shape, gravity tries to flatten the droplet, especially for larger volumes. We use the dimensionless bond number to quantify the relative importance of gravitational forces versus surface tension forces. Bond number equals rho gl squared divided by gamma, where rho is density, g is gravitational acceleration, l is characteristic length, and gamma is surface tension. Large droplets with bond number much greater than 1 are flattened by gravity. Small droplets with bond number much less than 1 maintain nearly perfect spherical shape. This raises an important question. What is the critical droplet size where gravitational distortion becomes negligible for optical applications? The capillary length, Lc, equals the square root of gamma divided by rho g. For water, this is approximately 2.7 millimeters. Below this size, surface tension dominates. Now we arrive at the revolutionary technology, electrowetting. This allows us to electrically tune droplet shape and thus focal length dynamically. Electrowetting on dielectric, or EWOD, uses electric fields to modify the apparent surface tension, changing the contact angle reversibly. The Lippmann-Young equation describes this. Cosine theta at voltage V equals cosine theta 0 plus epsilon 0 epsilon r divided by 2 gamma d times V squared. With zero voltage, the droplet has a natural contact angle determined by material properties. The droplet sits on a thin dielectric layer above an electrode. When voltage is applied, the electric field modifies interfacial energy, reducing contact angle. The droplet spreads, becoming flatter with longer focal length. Practical electrowetting lenses achieve focal length changes of 50% or more, with response times in the millisecond range. For robust devices, we encapsulate droplets between substrates or within chambers. This prevents evaporation and provides mechanical stability. A typical encapsulated design has transparent windows top and bottom, with the liquid droplet suspended between them. An aperture defines the clear optical zone. Advanced designs use two immiscible liquids with different refractive indices. The interface between them forms the tunable lens surface. The conducting liquid at bottom and insulating liquid at top create a deformable interface. Voltage changes interface curvature without moving the droplet center. Droplet lenses enable revolutionary microcamera designs. Smartphone cameras increasingly use liquid lens autofocus for compact, fast zooming without mechanical parts. Compared to mechanical voice coil motors, liquid lenses offer faster response, no moving parts to wear out, lower power consumption, and smaller package size. In a smartphone implementation, the liquid lens sits above the CMOS sensor. Electrical control provides autofocus in under 10 milliseconds. An important question: what factors limit the optical quality and resolution of droplet lenses compared to solid glass optics? The answer involves spherical aberration, since simple droplets are spherical, not aspherical. Interface vibrations and temperature sensitivity also affect image quality. In microfluidic systems, droplet lenses enable on-chip magnification. This brings microscopy directly to biological samples without bulky external optics. A microfluidic chip integrates sample chamber, droplet lens, and photodetector. The droplet can be tuned to focus on different sample planes for three-dimensional imaging. Droplet lenses in lab-on-chip systems typically achieve magnification from 5 times to 20 times, sufficient for cellular imaging. Magnification M equals 1 plus D divided by F, where D is the distance from lens to sensor and F is focal length. Tuning F changes magnification. Perhaps the most sophisticated application is adaptive optics. Arrays of droplet lenses can correct wavefront distortions in real time. Ground-based telescopes suffer from atmospheric turbulence that blurs images. Traditional adaptive optics uses deformable mirrors, but droplet arrays offer an alternative. A droplet-based deformable mirror uses an array of individually addressable droplets. Each droplet's curvature is controlled by local voltage, creating a pixelated wavefront corrector. With response times under 1 millisecond, these systems can track and correct atmospheric turbulence at hundreds of hertz update rates. Let's examine quantitative performance metrics. We'll plot how focal length varies with voltage for a typical electrowetting lens. This graph shows focal length versus applied voltage. At 0 volts, focal length is 8.5 millimeters. At 90 volts, it decreases to 2.2 millimeters, giving a tuning range of over 4 to 1. Here's a question to test understanding. Why does focal length decrease when we apply voltage? The answer: electrowetting flattens the droplet, increasing its radius of curvature. Since focal length is proportional to radius, a flatter droplet has shorter focal length for the converging side. No lens is perfect. Let's analyze the primary aberrations that limit droplet lens performance and how we can mitigate them. Spherical aberration occurs because rays far from the optical axis focus at different points than paraxial rays. This is inherent to spherical surfaces. The focal shift delta F is proportional to r squared, where r is the radial distance from the optical axis. This quadratic dependence causes blur. Parallel rays entering at different heights converge to different focal points. Marginal rays focus closer than paraxial rays, creating a focal spread instead of a sharp point. We can mitigate spherical aberration by using a small aperture stop to block marginal rays, or by designing a spherical correction elements in the optical train. The speed of lens tuning depends on surface tension dynamics. Let's analyze the time-dependent behavior. The characteristic relaxation time tau equals eta r divided by gamma, where eta is dynamic viscosity, r is droplet radius, and gamma is surface tension. For water droplets of millimeter size, the relaxation time is approximately 1 millisecond, enabling kilohertz switching rates. This graph shows the temporal response to a voltage step. The focal length changes exponentially with time constant of about 0.8 milliseconds, reaching 90% of final value in 2 milliseconds. An important design question: How does liquid viscosity affect both optical quality and response time? Higher viscosity liquids are more stable against vibrations and gravity, improving optical quality. But they respond more slowly. Engineers must balance these competing requirements. Cutting-edge research explores multi-droplet systems where arrays of lenses work together to create complex optical functions. A lenslet array consists of multiple droplets arranged in a regular grid. Each droplet can be independently controlled, enabling complex wavefront shaping. These arrays enable light-field imaging, where both spatial and angular light distribution is captured, allowing post-capture refocusing and three-dimensional displays. Temperature affects refractive index, surface tension, and viscosity. Thermal stability is critical for precision applications. The thermo-optic coefficient dN by dt is approximately -10 to the -4 per Kelvin for most liquids. This means focal length shifts with temperature. This plot shows refractive index versus temperature for water. The linear decrease of about 1 part in 10,000 per degree requires temperature stabilization for high-precision systems. High-performance systems use either active temperature control with thermoelectric coolers or optical compensation schemes that correct for thermal drift. Let's discuss how droplet lenses are actually manufactured and integrated into devices. The fabrication process combines microfluidics with electronics. Manufacturing involves microfabricating the lens chamber, typically using photolithography and etching. Then liquids are dispensed and the device is hermetically sealed. The layer stack includes electrodes, dielectric insulation, hydrophobic coating, and a liquid cavity. Each layer requires precise thickness control and material selection. Manufacturing challenges include preventing liquid evaporation over product lifetime, maintaining chemical purity, and ensuring electrical insulation doesn't degrade with voltage cycling. How do droplet lenses compare to traditional solid glass or polymer optics? Let's make a quantitative comparison. Droplet lenses offer tunability and fast response, but with higher aberrations. Glass lenses have superior optical quality, but require mechanical motion for focus adjustment. Droplet lenses are ideal for applications requiring compact form factor, electrical control, and adaptive behavior. Glass remains superior for fixed high-resolution imaging. What does the future hold? Current research explores several exciting directions that will expand droplet lens capabilities. Researchers are developing techniques to create spherical droplet profiles using non-uniform electric fields or shaped substrates, reducing spherical aberration. Chromatic aberration correction through multi-liquid stacks with compensating dispersion, enabling color imaging without aberrations. Machine learning algorithms that optimize droplet array configurations in real time for specific imaging tasks, creating smart, adaptive optical systems. Development of biocompatible droplet lenses for intraocular implants that could restore accommodation in presbyopic patients, replacing rigid artificial lenses. Energy efficiency is critical for battery-powered devices. Let's analyze the power consumption of electrowetting systems. The energy per switching cycle equals 1/2 CV squared, where C is electrical capacitance and V is applied voltage. For a typical device, capacitance is 10 nanofarads and voltage is 50 volts. This gives energy of 12.5 microjoules per switching event. At 1 kHz switching rate, power consumption is 12.5 microwatts, negligible compared to image sensor power. Electrowetting is extremely energy efficient. Here's an interesting question. Why is electrowetting power consumption so low compared to voice coil motors? The answer: electrowetting only requires energy to charge the electrical capacitance during transitions. No current flows in steady state, unlike motors that fight mechanical loads continuously. How do we quantify droplet lens performance? Several standardized metrics assess optical quality. The MTF measures contrast as a function of spatial frequency. It quantifies resolution and aberration effects comprehensively. The green curve shows MTF for a nearly perfect lens. The red curve shows degradation from aberrations. The 50% MTF point defines practical resolution limit. The strial ratio compares peak intensity of actual point spread function to the theoretical diffraction limited peak. Values above 0.8 indicate excellent optical quality. Root mean square wavefront error quantifies phase aberrations. For diffraction-limited performance, RMS wavefront error must be less than lambda over 14. Let's conclude by summarizing the key physical principles and practical applications we've covered. Droplet curvature, governed by surface tension and contact angle, naturally creates a lens with focal length inversely related to curvature. Material refractive index determines focusing strength. Higher index materials provide shorter focal lengths for the same geometry. Electrowetting modifies contact angle electrically, changing droplet shape and thus focal length reversibly with millisecond response times. Proper encapsulation prevents evaporation, enables two liquid designs, and provides mechanical stability for practical device integration. Droplet lenses find applications in smartphone cameras, lab-on-chip microscopes, adaptive optical systems, and emerging biomedical implants. The future promises spherical designs, multi-wavelength correction, AI integration, and biocompatible systems that bring droplet lens technology to new domains. I leave you with a final question. Given these capabilities, tunability, compactness, speed, and low power, what new applications can you envision for droplet lens technology?